I wanted to just take some time today and walk through, I want to walk through all of the ones from 5.2a so that you can make sure you did them right, so that you're feeling good. I want to hear from you as to what your strategies were that worked. And kind of off on the side here, I will continue. So maybe I'll scoot this over a little bit. Maybe you can see that a little bit. Kind of jot down some ideas as to what works. And then we'll see what else we can do. I've got some more practice for us today. And I really just want you to start getting comfortable with it. This is not something we're necessarily going to master on day 1 or day 2, and that's okay. It's really just, let's realize that we can use the identities that are on that trig cheat sheet, so have that out, again, if you think it's helpful, to just write things however we want and come up with some good strategies on how to do that. And a lot of those same algebraic strategies can be applied to all sorts of stuff, right? So off on the side here, I'm just kind of rewriting what I wrote last time. Kind of our plan, what we want to do for these kind of things so that we can go back to it, right? I want to make the left and the right side identical. So I just said make the left equal to the right. Doesn't matter which one you work with. You'll see though, usually it's the left side that they start with being much more complicated. And then we end up just making it look like the right. And sometimes, and really most of the time, we never even touch the right side of that equal sign. And it really only takes those handful of identities, the reciprocal ones, the tangent and cotangent ones, and then the Pythagorean ones, okay? And then just a little bit of algebraic skills that you already know how to do, factoring or multiplying or whatever it is, right? So if I can make the left and the right side the same, I know I'm good. Don't move anything from the left to the right or right to the left. We're kind of imagining that there's kind of some physical separation between those two. I just don't want to move anything around. And right, my goal is to get them to be exactly the same. So I'm going to simplify one or both sides separately. And I usually always kind of start on the complicated side. So start on the complicated side. And we already wrote that down. So. But I wanted to maybe add today to our list of strategies as to how to get these done. And I'll just walk through them again. I know that we did these first couple, but I just want to make sure that we talk about them again, right? Because we saw them last time, and but make sure that we got them. So I would love to hear from you. Something like number 1, what is a good way to start if your largest exponent is equal to 1. So that's what I wrote over there. If your exponents equal...
Set them equal to cosine or sine.
Yeah, rewrite everything in terms of sine and cosine, right? If you don't have any exponents, it's a really good place to start. Now, maybe it doesn't work, but most of the time it can be really helpful. Now that does start initially potentially to make things a little bit more complicated. Like right now I don't have any fractions, but the moment that I write something like secant as 1 over cosine, right, now I have a fraction. So temporarily, yeah, this seems a little bit more complicated, okay, and that's okay. And that's kind of the only downfall that I see to that first strategy, that if your exponents are equal to 1, rewrite as cosine and sine. Okay, rewrite everything in terms of cosine and sine. And then whatever happens from there, I kind of like, I use an identity and then I do some algebra. I try to see what happens. And with this first one, what we saw is that the cosines could cancel out because you have 1 on the bottom of a fraction and 1 without a fraction, which means it's on top over 1, right? And then there we go, 1 equals 1, done. I put a little check mark next to it if you like that idea. You don't have to. But I usually like to just kind of indicate that I did what I wanted to do. I made it. You can even put QED, right? I did it, right? The word verify could easily be replaced with the word prove, right? Prove the following trig identities, okay? And that same strategy worked really well with number 2 as well, right? Because we had tangent of x, okay, so that's sine of x over cosine of x. And remember that when we saw this stuff on Friday, to limit the messiness of all of it, a lot of times we drop the parentheses around the inputs as long as they're monomials. So sine of x or sine of 2x or 5x or sine squared x or anything like that. We don't need the parentheses to indicate that it's sine of x the function, right? Now, if you want to keep doing it, of course, you always can, but I just wanted to let you know that that's okay if you don't. Okay, and then cosecant is 1 over sine. And then we wanted to make that, hopefully, into secant. And what we saw is by doing that, it allowed us to recognize the simplification that can happen that maybe you wouldn't otherwise notice, right? I don't necessarily notice that tangent and cosecant are going to be able to combine nicely together, right? And if I can make 2 fractions into 1 by multiplying the tops and multiplying the bottoms, even better, right? And then 1 over cosine is secant. And the reason why, for me, I liked rewriting the left side as secant rather than writing the right side as 1 over cosine, although either one would be fine. The simplest version of anything doesn't contain any fractions. And I know that these are identical, right? They're equivalent to one another, but this is the simpler version because it's not a fraction. So that was just kind of a choice that I made to do that. Cool. So we did those together, so I just wanted to refresh that. I know we did number 3 together as well, but that one was a little bit different. So I'm going to scroll down to there. And then I don't remember if we got all the way through number 4. I think we did it pretty quickly, so I want to make sure that I do that. Number 3 and number 4 have something happening that the other ones didn't, right? We have exponents bigger than 1. So if your exponents are larger than 1, the first strategy that we saw, okay, was this one. So I'm actually going to come in here. I'm going to indent this one. Use a Pythagorean identity. Because you're going to see that once our exponents start to go up, our options for what to do also go up. It doesn't have to be a Pythagorean identity that I use first. There might be something else that comes up that could work as well. More of an algebraic idea first. So sometimes we jump in and we say, I'm going to use an identity. I'm going to go to my trig cheat sheet. I'm looking at those top 3, and you can see that there are a heck of a lot more. We're not going to do any of those necessarily with the multiple angles, and there's a lot we can do. They're a lot of fun. They're just little puzzles. That's really all it is. When we look at something like this, cotangent, cosecant, both of them being squared, I see that square and I think identities, and I think those Pythagorean ones. And so that's what I do, is I look for one of those 3. Right, either the sine and cosine one, the tangent and the secant, or the cotangent and the cosecant. And remember that those 3, certainly specifically more than the other ones, because you have more than one term on one side, right? You either have sine plus cosine, or you've got tangent plus 1, or you've got 1 plus cotangent. You may want to move some stuff around within those given identities to make it look the way you want. Maybe you want to get, let's say, sine squared by itself in the first Pythagorean identity. Well, okay, so call it 1 minus cosine squared, right? You can move stuff around within those identities to make them work however you want, okay? And so when I look at something like number 3, I see cotangent and I see cosecant. They're both squares. It really doesn't matter which one that I go with, because the cosecant squared is the one that's kind of already isolated in my, so when I go like this, I'm pointing at my computer because that's where my trig sheet is. That's the one that's already by itself. And so I'm going to replace this right here with the other side of that identity because they're the same. So I'm going to bring down that cotangent squared x minus, and here's where the replacing is going to happen, right? I'm going to drop that version of cosecant squared, which is, just to switch colors so you can see it, 1 plus cotangent squared. Right? Those are the same. And I've used an identity. And so I kind of want to see where that gets me. I want to kind of allow the algebra or something to happen here now that I've done that. And so I guess I'll get rid of parentheses to see what happens, right? I'll allow the subtraction to happen everywhere. Cotangent squared equals -1. Again, working on the left side, working on the complicated side, trying an identity and seeing what happens. And there we go, right? Cotangent minus itself, perfect. So the only thing that I'm left with is -1, and the right side is already -1, and so on. Again, stop me if you have questions. but hopefully talking these through will kind of help see where we're at. Okay, all right, cool. So those are the three we did. I wanted to do those with you. All right, now talk to me. I know we might have started number 4, but maybe we don't remember. What do you think we could do with number 4 by using an identity first and trying to simplify?
We could change the 1 to sine squared x plus cosine squared x.
This one right here, right, has that cosine squared in it. And so that's a little clue for me that maybe a Pythagorean identity could work really well. And so if you look at that first Pythagorean identity, sine squared plus cosine squared equals 1, there's a 1 right there that I can quickly and easily replace it with, yes, for a moment, something else slightly more complicated. Right, so that 1 right there, I like it, becomes sine squared x plus cosine squared x. And then I just kind of bring down the rest. That's the only identity that I'm going to use at this point. And so when you're contemplating, should I change everything to sine and cosine, or should I go with a Pythagorean one? If you've got larger exponents, go with that first. Try to deal with those bigger exponents and see what happens. All right, so I'm going to bring down the minus cosine squared. Now that's all in that first set of parentheses, right? Now that's being multiplied through cosecant x, and it's supposed to be equal to, I'm falling off the edge there. Well, you know what that right side's supposed to be. So I'm just going to say equals, you can write in that sine x. And look what happens in there. Perfect. Right? There's something we can do algebraically once that happens. And so on the inside here, I've just got sine squared x left over, and that's times cosecant x. Okay, now I've got some space. Now I want it to just end up being sine of x. And that's the one thing that I think I really like about these kind of identities, verifying them. You know what the end result is going to look like. Like for Christmas, Santa brought my daughter some puzzles, some 60-piece puzzles. And when you take the puzzle pieces out, there's a picture of the completed puzzle behind it, like a little piece of paper. And so you know where things are supposed to go, and you know what that finished product is going to look like. That's kind of like what the right side is here. I've got a goal. I've got a target that I can try to shoot for. So, all right, we used a Pythagorean identity. Great. It did its thing. Okay. Now what? I certainly don't want to go back and call that 1 minus cosine squared. That would just be undoing all of the hard work that we just did. Let's try something else. What else do you think we could do now?
We could change the cosecant to 1 over sine.
Let's use the other strategy that we've gotten so far, right? Let's try calling cosecant. So I'm just going to change my parentheses to a dot here for multiplication. 1 over sine x. Again, just kind of bringing that right side down. Cool. Now what? What do you see? Again, just working on that left side that maybe we can do to make things simpler. It's always kind of the goal, right? I want to make things simpler since my right side is plain old sine of x. Maybe that helps. Now, if you're dealing with fractions, go ahead and write everything as a fraction if you think that might help.
We could cross reduce or multiply straight across.
So you could call it, if you wanted, sine squared on top and then sine of x on the bottom. If you'd like to combine fractions, great way to do that, right? When we're multiplying, super easy. Just multiply the tops together, multiply the bottoms together. Okay. Simplify. 1 from the top and 1 from the bottom, like it was x squared over x, right? And that means the only thing that I'm left with is a sine of x on the left and good, a sine of x on the right, and I'm done. Okay, so combining fractions is a really good strategy. I'm gonna write that one down, I liked it. I'm gonna leave a little space here in case we have some other ideas with exponents being bigger than 1. So I'm gonna say combine fractions. Now you can do that a couple different ways, right? I can combine fractions by multiplying. I could also combine fractions by adding or subtracting. I could also rewrite fractions as like, so if I have like a trig function on top and a trig function on bottom, I can rewrite it as multiplying by the reciprocal and kind of break those fractions apart. So it kind of works in both directions, which is really nice. Cool. So that one kind of challenged us a little bit because we had to use a couple different ones. I'm going to roll through this next one really quickly because it's really similar to ones that we've been doing. Again, stop me if you need me to. But with something like number 5, really similar to 1 and 2, right? Just seeing that there's no exponents bigger than 1, you might find that it's really easy to just rewrite that left side, and I'm only going to work with the left side first. In terms of sine and cosine, if you want to combine fractions, it's helpful to put them over 1 in case you don't have one, if you think you need to. I would love you to get to the point where that is not necessary, that you recognize that that's being over 1, and that you can just multiply the sine of x with the 1 on top, leave the cosine of x on the bottom, and I mean, there it is, sine over x. Sine of x over cosine of x, that's tangent. Right? You can box it into, that's fine by me. You don't have to put the check mark. You can just box it up so you know you're done. Cool. All right. Now what? Number 6, things start to get a little bit trickier because you've got cosine squared, you've got secant squared minus 1, and you've got sine squared. Pythagorean for sure with all those squareds in it, but which one should we try to use? Well, again, work with what's complicated first if you don't know where to start, right? If you're not sure what to do, first pick the complicated side. All right, so I look at it, left side, definitely more complicated than the right, okay? But on that left side, you've got the cosine squared and you've got secant squared x minus 1. Okay, so between those two factors, right, you've got the cosine squared x factor and you've got the secant squared x minus 1 factor. Work with the complicated one and see if you can do something with this. All right, work in there first. So starting with what's complicated. Always, always, always a good first strategy if you're not sure how to begin otherwise, okay? And so I look inside there, and I notice that, okay, secant squared x, nice. If I look at a Pythagorean identity, that one is already by itself in that second Pythagorean identity with the tangent squared plus 1. And so you can do one of two things here. You can replace secant squared with tangent squared plus 1, or you could look at that second Pythagorean identity and say, you know what? I can make it look exactly like this. So I'm just gonna temporarily, so don't write this yet. All right, here's my Pythagorean identity. All right, there's the one that I'm looking at on my trig cheat sheet. And I say, okay, yeah, secant squared already by itself. So I could drop tangent squared x plus 1 right here, and then just let the algebra take care of itself. Or I could try to make what's inside that red circle look like exactly like that. Can I find something that looks exactly like that? Well, if I slide that plus 1 over with subtraction, tangent squared x is secant squared x minus 1, right? We can manipulate the trig cheat sheet identities however we want. And usually it's just the Pythagorean ones that we start moving stuff around. But I can make secant squared x minus 1 exactly, right? I've got that exact expression that I can isolate. And so if I can do that, if I can get the identity that I'm working with to look exactly like an identity that I was already given, And it's kind of crazy that we only need these handful of identities. We can do so many more. Like you could look up like verifying or proving trig identities online. There are millions, like millions of these that you could work with, which is kind of crazy, right? We can do this right here and call that exactly, so I'm gonna bring down that, call that exactly tangent squared. Exactly. Now, maybe you just wanted to write it as tangent squared x plus 1 minus 1, and then let the ones cancel. That's cool too. Okay, that's just an extra step within the identity rather than an extra step messing around on your trig cheat sheet. That's your choice. Okay, either one's fine. Okay, cool. We've already used a Pythagorean identity. Seemed like a pretty good choice. Now, let's try the other one, right? So it's kind of, you're not always going to just, I'm going to use 5 Pythagorean identities over and over and over again and see what happens. Probably not going to happen. You're probably going to use one idea, see where it gets you. Oh, look, this is simpler. And then you try another one. Okay, well, let me try rewriting everything in terms of sine and cosine. Okay, so that's cosine squared x times, well, tangent squared is sine squared over cosine squared. And if that works, great. And if it doesn't, great. That's okay. We tried something. Okay, these are not going to be always quite so easy to see. The more practice you get with them, the better you'll get, right? Cosines are gone. Perfect. You want to put this one over 1 to make sure you see that? No problem. I think if you can recognize that when you multiply and divide by the same thing, those are going to cancel out. You'll be in pretty good shape. Done. Sine squared equals sine squared. Questions up to this point before we really just look at the last one that was just a little bit trickier. 8 hopefully went pretty well, but 7 could have been a little bit tougher. So I'll go through that one. Questions so far? Well, okay, cool. Let's do 7, which took us to a different looking setup because our exponents up to this point were either just 1 or 2. Now they're bigger. And that's okay, right? And so that's, if your exponents are bigger than 1, use a Pythagorean identity if they're equal to 2, right? If your exponents, I'm just coming over here for a quick sec. If your exponents are equal to 2, that's a great one to choose, right? But what you might think about doing with something like 7, of course, working on the more complicated side. And when I think complicated, the bigger the exponents, the more there's going on. So I'm thinking the left side again is probably going to be our more complicated side. Like that's not, those aren't Pythagorean. That's x to the 4th, or secant of x to the 4th, right? Tangent up to the 4th. That's not going to work. Pythagorean identities work when things are squared, and that's it. So what do you think we could do? Factor. Right? Now, you might not recognize how nicely this factors because of all the trig stuff. And so I want to do something just temporarily. Don't write this down unless you think you need it. I'm going to rewrite some things so you can see the factoring that's happening. Imagine this was just x to the 4th minus y to the 4th. Okay? Or P and Q, or W and U. You can pick any 2 letters you want to help you recognize this. And you'll actually start doing that, probably Calc B. We do something called U substitution to make the calculus work a little bit better when things are getting a little messy. So let's say I temporarily rewrite this like this. That's the difference of 2 squares, right? That is, square root of the first one goes first. Square root of the second one goes second. One's a plus and one's a minus. Right? Now, this is also factorable, right? Because that's still a difference of 2 squares, but I kind of just do one algebraic move here, and then I see what happens. And so what you're noticing potentially with number 7 is something that didn't happen yet. And this is not necessarily going to be just if exponents are bigger than 1. Sometimes you just factor as a really good strategy. So you know what, I'm not even going to put it down there. I'm going to put it on its own over here. Factor. Okay. Maybe you recognize the greatest common factor. I just wrote factor down there at the bottom as part of my strategies. Maybe you recognize the greatest common factor and you try that and you see if it works. Here you recognize difference of squares, or you recognize quadratics, right? Stuff like that. If you can recognize that, try it, right? So that's what I'm going to do. I'm going to make 2 sets of parentheses here. I'm going to make them a lot bigger because I got to take the square root of the first one and put it first. So that's secant squared. Secant squared. All right, square root of the second one goes second, so that's tangent squared. Tangent squared. 1's a plus and 1's a minus. And here's what I'm trying to get to, secant squared x plus tangent squared x. That's what I want to get to when I'm done. Okay, so now we kind of pause and we see what that did for us. All right, well, stop and take a look, unless you did this yourself and you're feeling pretty good about it. But if this is maybe the first time you're actually working through this this way, what do you notice about what's on the right side already, kind of our goal for what we're trying to get to, and what's on the left side partially? What do you see? What do you notice about the right side? And what that means for us on the left side?
They both have secant squared x plus tangent squared x.
There's my goal, right? Right there. I know that is what I'm trying to get to. And so I don't really want to mess with that at all, right? Remember what your goal is in mind, is to get the left and the right side to be exactly the same. So I always kind of keep an eye on that right side to give me a target, right? I want to get to the end of this puzzle. I know what that picture looks like. It looks like this. And so all I want to do is I want to mess with whatever is in there, and hopefully, if these are connected by multiplication, this had better become 1, because then if I'm multiplying by 1, then I'm good to go. Okay, nice. So leave that alone temporarily. Hopefully things worked out okay. And let's try to just work with what's in there, right? So I'm just going to bring this first set of parentheses down because that's perfect. That's exactly what I want. Okay. What do you think we could do with the inside of that second set of parentheses?
Tangent squared into secant squared minus 1.
Sounds good. So if we want to just mess with that, right, that tangent squared right there, because that, oh, sorry, the secant squared. So however you want to write it is kind of up to you. The Pythagorean identity that's given has secant squared isolated. All right, if you look at that Pythagorean identity, it's 1 plus tangent squared equals secant squared. And so if you don't want to do any of that manipulating of the given identities, then look for the term that's by itself. Okay, look for the one that's already isolated, which in this case is secant squared. So I'm going to replace that with tangent squared x plus 1. Okay, then I'll bring down this minus tangent squared right there, equals that. I'll save some space, save some time. All right, tangent squared minus, I want to switch colors, tangent squared minus tangent squared. There it is, right? Bring down the secant squared plus tangent squared. And yes, that's what I wanted. It was equal to 1. All right, what was inside there is equal to 1. I still have to take that last step. You cannot finish an identity until the left side and the right side are written out next to each other, identical sides, box it up, put a check mark next to it, whatever you want. It's gotta look like that at the end. As silly as that seems, you know, to say 1 equals 1 or 10 equals 10 or x equals x or whatever it is. Okay. And you see that I'm going back and rewriting in that right side. I don't know that you need to, right? Right? If you're, I mean, go back to algebra 1, like f of x equals some function, right? You say, oh, f of 3 equals, and you write it out, and then you do like step by step by step arithmetic. You don't always say f of 3 equals, f of 3 equals, f of 3 equals all the way down. You just save that for the last line. Same thing here. If you want to just hold on to the right side by leaving it blank, because we're not going to actually mess with that most of the time, you'll get to there, okay? 8 should be really similar to what we've been doing with like number 1, number 2. Right, change everything to sine and cosine, see what you get. So cotangent would be cosine over sine. Secant is 1 over cosine. The cosines would cancel out. 1 over sine. Okay, perfect. Cosecant. Okay. How are we feeling now? Do we feel better now than we did before? All right, some pretty good, some still hoping for some epiphanies. Okay, so what I would like you to try to do right now is to try numbers 1 and 2 from homework 5.2b. Okay, so attached to today's announcement is obviously sitting there as an assignment. Some of you are already on there working on it, so that's cool. Try those 2. Okay, I spread them out. You don't have to leave nearly as much space. I only spread them out on that Google Doc so that when I come up on the board, I have a whole bunch of empty space there. It won't take you nearly that much space. I want to do 3, 5, and 6 with you. Hopefully we can get those done. But try 1 and 2. You can even try 4. So let's do that. Try 1, 2, and 4. We've got those ideas down. Take, I don't know, 5 minutes. Something like that. Try 1, 2, and 4. I'm going to put 1 and 2 up right now. I'm going to work on those 2. So peek when you're ready. But I want to give you some time to try these things out. Now that you've seen a few with me, I definitely want to get a couple other strategies in your head in terms of what we can do with something like 3 or 5 or 6. All right, so try that. Let's see, it's like 9:08. Let's say like, I don't know. Yeah, let's try 5 minutes at the most, okay? All right, Pythagorean identities, if your exponents are equal to 2. If they're equal to 1, try rewriting them as sine and cosine and see where that gets you. All right, so there's 1 and 2. I think 4 will happen pretty nicely for you. So I won't put that one up, but let me know if you want to see it. as a little hint for number 2 as you're working through it, my right side only has sine in it as a trig function, so I had to make sure I got rid of cosine. All right. Left side had both sine and cosine, right side only has sine. And if the right side is my goal, I got to make sure I get rid of cosine by rewriting it in terms of sine. So that's why my side work there has me isolating the cosine squared from that first Pythagorean identity and then dropping it.
Mr. Rosengren,
Yeah,
is it okay if we solve on the right side to make it equal to the left side for number 2?
absolutely. You can work on either side. Definitely. So if you saw, hey, oh, look, 1. Oh, perfect. That's sine squared plus cosine squared. Great. Love it. Absolutely. You can work on that side if you want. Usually we try to make things simpler by limiting the number of trig expressions that we're using. So going from a side that has 2 different ones and trying to make that to just have 1 is sometimes crucial to how we actually end up using these, especially when we get to calculus. It makes the calculus aspect of all of that a little bit easier. It makes solving a trig equation a little bit easier because then you're just dealing with 1. You'll see that when we get to quadratic like trig equations, if you've got sine squared and cosine squared in a problem, then I can't factor it the way that I would normally like to, like I would a quadratic. It's like having x squared plus 2y minus 7. I can't factor things that have different variables in it, and cosine of theta and sine of theta are like having different variables. So yes, absolutely. If you're just asked to verify an identity, work with either side, whichever one works. But know that the plan for me with number 2 is to make things simpler by reducing the number of trig expressions that we're looking at. But yeah, that works. Okay, another moments, if you're still working on number 4, you can do that. And then I want to talk about 3, I want to talk about 5, and I want to talk about 6. I'll probably save 5 for last in case we run short on time. I definitely want to do 5, 3 and 6. Okay. Does anybody need another moment? I still see people writing some things down. Look up at me when you're done so I know I can keep rolling. Okay, keep working. Slide this over. There we go. Again, you can try the other ones before I get to them, but some things happen with 3 and some things happen with 6 that I just want to make sure we talk about as options. All right, I'm gonna roll on here. Hopefully that worked out okay. I'm gonna move on to 3. I'm gonna do that one with you. Stop me if you need anything. All right, number 3. Okay, again, I want to work with the left side because it's more complicated. It's got parentheses, it's got 2 binomials being multiplied together. Now, sure, could I call the right side, okay, cosine squared? Sure, I could get a Pythagorean identity going there and I could mess around with stuff like that. That would be fine. But just for the sake of trying it out and to show you that this is another strategy, in case you get stuck for ideas, because the strategy you could use on the right side, use a Pythagorean identity and then see what happens, okay? With the left side here, because we've got those sets of parentheses and there's no exponents bigger than 1, we really can't do any kind of factoring or Pythagorean identities. Everything's already in terms of just sine on the left-hand side. So what do you think? What do you think we could do on the left-hand side to try to make it look like the right.
Multiply and then use a Pythagorean identity.
Right? Actually multiply. Right? If you've got parentheses, try, I'm just going to say like distribute. And see where it gets you. Right? Okay, so 1 times 1 is 1. Minus sine of x, I'll write it out. Plus sine of x, even though I know that those are about to cancel. Let me slide it over a little bit. Let me give myself some space. 1 minus sine of x plus sine of x minus sine squared x. We want that to end up being cosine of x, right? And those middle terms are going to cancel. If you recognize the way that that's factored, that is the factored version of the difference of two squares. So it doesn't surprise me that we end up with the difference of two squares here on the left when we're done. The first one squared and the second one squared, right? Just kind of the opposite of factoring. And there it is. There's, like, that is the identity, right? That is kind of the re-situated version of that first trig identity. If you really want to do it out the long way and say, you know what, I'm just going to change the number 1 into sine squared x plus cosine squared x, you will always, always get yourself to the correct answer, no matter which version you use of those Pythagorean identities, because the things that you want to cancel will cancel no matter what. Okay? Beautiful. Okay, so sometimes factoring is a great way to do it, sometimes unfactoring, right? Multiplying stuff out, maybe that's a great way to do it. Cool. Number 4 is just change everything to sine and cosine, right? Because there's no exponents bigger than that. So 1 over sine, sine over cosine, sines will cancel, 1 over cosine, perfect. You get to that secant. Okay, so just a couple steps there. Most of these trig identities are just a handful of steps at the most. I could get super, super crazy and get like ultra complicated with them. But the thing that I want you to get out of this experience between Friday and today, and maybe tomorrow, we'll see, maybe we'll start it off with a little practice so you can see it, is to learn that it's okay to move stuff around, to get comfortable replacing one trig expression with another, because they're all so related because of how connected trig is. All right, really cool. All right, so I'm gonna get rid of this one. I want to talk 6 next before we do 5. Take a look at 6. Left side, obviously the more complicated one. It's got fractions, and I got to add them together. So, but you've got 1 plus cosine of x on the bottom of the first fraction, and you got 1 minus cosine of x on the bottom of the second one. And because those denominators are different, I can't add the fractions yet. All right, we need common denominators to add and subtract fractions. And so how do we do that? I'm gonna come all the way over here so I've got some space. 1 over 1 plus cosine of x, there's my first fraction. I have to create common denominators. How should I do that? Since they don't have anything in common, there's no common factors, right? 1 plus cosine x, 1 minus cosine x, those are totally different. How do you add fractions to 7ths plus 3/5 whose denominators have no common factors? Separate.
Cross multiplying?
Cross multiplying is when you have two fractions equal to each other.
Oh, my bad. I guess add, wait, it was add them, my bad.
Right, I want to add these two fractions. So if I'm adding fractions, like imagine it's 2/7 plus 3/5, let's say it's the same problem.
Like add the tops together and add the bottoms together.
No, it doesn't work that way, unfortunately. I wish it would. Yeah, the answer wouldn't be exactly what we wanted it to be.
Oh, never mind.
We got to take the same pieces of the same size pieces of puzzle. If I've got 2/7 over here and I've got 3/5 over here, I've got apples and oranges. I can't combine those together and talk about how many oranges I've got or how many apples I've got. I got to put them together. I want to slice the things up into the same pieces by creating common denominators. Right? So I've got my 2/7 piece, I've got my 3/5 piece. How do you create common denominators?
Multiply the denominators by each other.
Good. But if I'm going to multiply this first fraction by 5 on the bottom and this second fraction by 7 on the bottom, the denominator of the other one, I don't want to put like a 1 or a 1 or a 2 and a 2 or a 3 and a 5 or whatever it is. I have to make sure that I don't change the size of my fraction. I want to make sure that I multiply by 1 through both by making sure I multiply the top and bottom by the same thing. Because when I do that, then I'm just multiplying, like there's 1, right? There's 1 right there. Okay, cool, nothing really changed. I'm just rewriting the way it looks. And so when I multiply this first fraction by the denominator of the second one, I have to make sure I do it on top and bottom, okay? And I'm going to do the same thing with the second one, plus 1 over 1 minus cosine of x. So kind of the original stuff in red there, the change that I'm making happening in blue. And let me ask you this as I kind of finish writing this up. Look at those two denominators. 1 minus cosine x and 1 plus cosine x. What would you call the relationship between those two? Two terms where the sign in between them is the only thing that changes.
Reciprocal?
No, that's when we flip them. Close. I know what you're thinking, I think. Think back to complex numbers. Section 2 point something. Honors pre-calc.
E?
No.
Oh.
Those denominators, conjugates of each other. And we know that we multiply conjugates of each other, that those middle terms on the inside are always going to cancel out, right? When we had, 5 plus 3i, and we wanted to get rid of the i's, we just multiplied by 5 minus 3i's. And there's so many applications of why conjugates in general are really, really nice to work with. It's because all of those terms on the inside are always going to disappear, right? So when I multiply across the top here, well, 1 times that, okay, so 1 minus cosine x. When I multiply at the bottom, okay, 1 times 1 is 1, minus cosine x plus cosine x, gone. I'm not going to bother writing it this time. And then minus cosine squared x. And that's the point, right? Multiplying by conjugates. Now, it happened this way on purpose. I picked this one as a great example of that. But anytime you want to start working with getting rid of fractions, potentially, multiplying by conjugates, especially of the denominator, is a great way to do that, just like we did it with complex numbers, trying to divide them, right? Same thing on top here, except it's 1 plus cosine x. The denominator, of course, is the same. We created common denominators. Okay. And in order to make these two fractions go together, that's why we did that. So let's actually do it, right? I don't need two separate fractions now. The idea of doing this, combining fractions, is just what I circled over there on my strategy. That's what I wanted to do. 1 minus cosine squared x. On top, 1 plus 1, okay, that's 2. Give me like 30 seconds. Negative cosine x plus cosine x, 0 cosine x. That 2 just shows up right on top. Okay. Ugh, still have a fraction though. Well, what is 1 minus cosine squared x?
Sine squared?
That's sine squared, right? And the more you start recognizing versions of those Pythagorean identities, even better, right? Because it's sine squared plus cosine squared minus cosine squared. And it's all gone. I'm coming this way just because I'm out of space. I can do maybe one more down here. That's 2 over sine squared. And I'm supposed to be at 2 cosecant squared. Right now I'm coming this way. You guys can go down.
What's the relationship between sine squared and cosecant squared? They're reciprocal over there. 1 over sine squared is cosecant squared, and we're there. If you have a denominator that is the reciprocal of something else, get it out of the denominator and take the reciprocal, right? 4 divided by 1/2 is the same as 4 times 2, right? Same thing here. 2 divided by the reciprocal of cosecant. Okay, so 2 cosecant squared x, which is 2 cosecant squared x. Voila, there it is. Time's out, so I can't do number 5 with you, but that kind of actually led you into it. When you do number 5, you've got a denominator of cotangent. Write it as multiplying by the reciprocal. Don't divide by 1/2, multiply by 2. Don't divide by cotangent, multiply by its reciprocal. Multiply by 2. Try that, okay? Finish this one up if you can. Get that uploaded to Canvas today. Nothing you have to do between now and then besides that. And I will see you tomorrow, same time, 8:35.
Thank you. Have a good day.
Thank you.
Thank
you. Bye.
Goodness, this entire day I've been messing stuff up. But
Oh, with the reciprocal, you mean?
well, this class would honestly be so much easier if we were in person.